So we have been working with logarithms for a little while. We're going to add now a new parent function to our repertoire. So if you recall back last quarter, we looked at several basic graphs. You got lines, parabolas, we did exponentials, square roots. Here's another one. Now that we know what a logarithm is, an inverse of an exponential, we can see what sort of shape and what properties this graph has with itself. So new parent function, f of x equals log base b of x. So let's hop over to a Desmos, see what it looks like. Now to get your log with a base, go over here to where it says functions. So pull up your calculator, choose functions, go to miscellaneous. And the one you want is this one right here. Now actually do this. Take a moment, get your Desmos open, get your logarithm in. And let's choose a base. How about like a base like 2? It's a good one to start with. Now the only restrictions on your base are that you have to use a positive number and it can't be the number 1. So if instead of 2 we use a 1, you'll notice there's no graph. It doesn't exist anywhere. And if you try and use a negative number, again, there's no graph. It doesn't exist anywhere. So it does need to be a positive number that isn't 1. And I'm going to switch to like a red so it's easier to see. And here's what your basic log graph looks like. So what I see is as you approach 0 from the left-hand side here, your graph goes down very, very quickly. The graph actually won't ever get all the way over to 0 for an x. And as you move to the right, your graph keeps going up, just not very quickly. So what we see is at the start here, your graph goes up fast, 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 but then it slows down its rate of increase as you go. So that's what a typical log graph looks like. And do some experimentation. Change the 2 to a different number. If we go like a 3 or a 5 or an 8 or an 8e. There are some similarities between all those different graphs and also some differences. I'd like you to do a little experimentation. So change this log, actually type the letter B, add in a slider, and then move your slider around and just see what impact changing the base has on it. I'm even going to encourage you to change the limits of your slider. Have it go from 0 up to like, I don't know, pick a 10 or a 20 or something like that. And then just play around with it for a little bit. Do a pause, come back in a moment. So here's what I hope you saw. Regardless of what happens, we do see some things happening all the time. Now there's 2 different types we get. I'm going to call this the upside down type, but most of the time they look like this. I'm going to call that the right side up type. So some properties. All the graphs have a vertical asymptote here at x equals 0, meaning they get very, very close to that x equals 0 line, but won't ever actually touch it. You're either going to go down very quickly forever, or you go up very quickly forever. All the graphs are defined only where x is positive numbers. So I'm going to hop back over here for a moment, because that's a description of the domain. Domain is the x values you're allowed to use. What we saw was that the x values on this graph are all positive numbers. So you can write it this way. You could also write it this way. That's the same thing. Or if you're using interval notation, round it and put a 0 and an infinity rounded on both sides. This is 3 different ways of saying the same thing. They all mean only positive x values are allowed to be used. As far as the range goes, the graphs here go down forever, but they also go up forever, even though they don't go up very fast. Even if you have a small base, your graph goes up forever and also is going to go down forever. So your domain is only positives, but your range, your y values, all real numbers. So you can write it this way. This symbol, an R with an extra line, means all real numbers. You could also say negative infinity less than y less than positive infinity, or an interval notation, negative infinity to infinity with rounded parentheses on both sides. These three also all mean the same thing. X can be only positive numbers, Y can be anything. Now, as we take a look at the graph, regardless of what base you pick, this graph is always going to cross the x-axis at the same spot, and it's right there. The x-intercept is going to be at 1, 0 all the time. Now, don't be surprised if I ask you why at some point. Why is it that 1, 0 is always a point on this graph, regardless of what the base is? 1 for the x, 0 for the y. Think about that. Check in with a friend or neighbor, have a little conversation, see if you get it figured out, because one of these days I'm going to ask you about it. And lastly, we did say there was going to be a vertical asymptote. That's that vertical line that your graphs get close to but don't ever actually touch. That's going to occur at x equals 0. So the y-axis here, our graph is going to get very close to it but never touch. And if we have a base on the other side, same thing in the other direction. You're going to get very close to this y-axis but never actually touch it. So down here, there are really two different styles we saw. If your base is small, a fraction or decimal between 0 and 1, then what you get is a graph that kind of looks like that. Right? That's the one where it's coming down. The general log graph, though, the graph that I want to be in your mind when you think about y equals log base b of x, is this one, the one that starts down low, comes up fast, goes through at 1, 0, and then grows, but very slowly as you're moving on. So this shape is what I want you to have in your mind when you think of the graph of a log function.